All right, so I think we're back in business here. It just took me a little while to get this Zoom to cooperate with me. I think there's another class that I had on my Zoom. So welcome to ENE350. You guys can all hear me. Let me just bring my camera a little bit. I had to switch my place to up here in order to actually be able to do this Zoom class. Let's see, there are some people who are waiting. All right, let me just start admitting them. Okay, very good. So we do have some students coming in. I assume that everybody else is in there. Nobody else is left out. Let me turn my lights on here because I think there's a lot more light coming from behind. All right, so this is our first class, and we're going to get started now. The way I'm going to do this class in terms of technology, I had some issues with the internet earlier, but hopefully we'll overcome those. What I'd like to do at this point in time is to see if I could actually do something that's going to bring and I'm sharing I need to share my screen, by the way. Let's go ahead and do that. So now you see my screen, everybody. And all I need to do is just so like I bring this iPad here, and let's see if this actually kicks in. It did come up for a second. Let me see if I just have to actually fire this up here. Okay. There's a technology that wants me to. Okay. That should hopefully happen in just a second. There you go. What you see there is actually my iPad. And everybody can see the iPad. Anybody can sound back? Sort of, right? What I'm going to do, I'm going to bring up this particular thing here. And are you able to sort of see what I'm able to see on my screen?
Yeah, we can see it.
Wonderful, wonderful. Okay. So I think technology is sort of complete at this point in time. And, as I said, it took me a little while to get everything kind of organized. I do have an Apple Pen here. As you can see, I'm not advertising this, but it is what I'm going to use. And I'm going to make this go a little bit this way so I can actually write it. So as I wrote, I was just playing with it last night to see if I could actually make this happen. It seems like it's happening now. I can make this a little bigger, but I don't think that I need to make it any bigger. And so this is ENE350 computer organization. This is, I guess, our two sections, 201 and 202. If you're actually in one of those two sections, then you're at the right place. And we're going to conduct our classes on Zoom, as you can see. There are a lot of places that, when I say a lot of places, there's an Elm site. Let me just say that. Okay. So we have an Elm site. That's just going to take a little bit getting used to this. Okay. We have an Elms site where there is a lot of documents and videos. So this is all related to the class. Now, what happened about 2 years ago, I guess, almost 2 years ago, I taught this class on one of the in one of the I guess the video rooms of University of Maryland, and they recorded all these lectures of mine, and they made them available through this ENE350 Elms site to my students. At that point in time, they were able to view this. Since I've been doing this class for some time now, for quite a while, what that means is that you actually, we will more or less repeat what I've been doing in this class as well. And so a lot of those videos actually are very relevant to uh, what we will do in this class. So I would recommend heartily to everybody. Uh, by the way, are we recorded on this? I don't know if I'm actually recording this because
It
I
looks
did
like you're
have.
recording. We have the
I think so.
recording.
If you look at top left, there's a like red light. Those is top
Yeah,
left.
I wish I could see that myself, but I don't actually see it. So you see that? Yeah, it's on the yes.
Yeah, it is
Right now,
recording.
it is being recorded. Good.
Yeah.
I'm glad that it is being recorded. So that way you also get a copy. Good to see you, Shaman. Yeah.
Nice meeting you.
Yeah, wonderful. All right. Good to have you back in ENEE350. So, so basically, you will have these videos that we're recording as we speak, and you'll have my renditions of my video renditions of my earlier class. I think that's from fall 2019, most likely. So, not quite 2 years yet. And so this is about logistics a little bit. Now, I do have a syllabus here. So one of the nice things about this way of doing things is, if I could ever get to it, um, you get to see my screen. This is what I like much about Zoom. I don't have to be, even though I could also place things into, when I share, I'm sharing my desktop. So whatever I get to see, you also get to see. And I just want to speak a little bit to the syllabus. It's so early in the semester and we're just starting our class. And what that means is, maybe it's worth just like looking at the actually word is open behind. This is one of the things that happens with this, is that I have to be cognizant of the fact that this guy is actually right there. So let me see if I could go back to this particular place. It'll take me a little while to get used to this. Okay, so here is the syllabus that I just emailed everybody. I assume that you guys all have it. Again, I just have to play with this a little bit to be able to see this. This has to go to the background that once in a while. All right, so so this thing I just want to talk a little bit. I guess since you guys are all here, you don't really need the link that I just shared here. Okay. The reason that I did this in two pieces at the time that I was actually creating these Zoom classes, and I guess Xiaomin has to also create his own editions, versions of his recitation or discussion classes. For some reason, Zoom did not let me to go all the way to the end of the semester, so I ended up basically splitting that between, I guess, today and March 31st, and then on to April 1st to May 11th, where our last class will be held. So you have a second link in there. I guess all of this will be made available to you somehow. I am assuming that will be transparent to you, so you don't really have to struggle to see exactly where the class is going to be held. All right. Now I said that we don't have a textbook. Sometimes I get students complain because naturally, we're all inclined to have our textbooks in front of us. We don't have a textbook in this class, unfortunately. There's no one particular sort of textbook that I would orient myself towards when I teach classes like this. And so this saves you maybe like, a few bucks here and there. You don't have to buy a textbook. And the downside of that is because you don't have a textbook, you may feel like, you don't have all the handles that you would need maybe to learn a material like this. However, that is really not been proven to be the case. In other words, I didn't have any serious issues. Always there's a couple of students who would certainly rely a lot more on textbooks than other students. There's plenty of information out there, and I don't think you will be in need of more information, if anything. And this is a sort of a hands-on class. That means we're going to do things together, or you're going to do things with Xiaomin in terms of like, programming assignments, some hardware designs, all those things will happen. And we have two technologies. I just have to do something about this thing that's actually hitting me from behind, the little fan that's kicking in. Just give me 1 second, and then I need to also grab my phone because I want to get on Elms as well to share with you a couple of things. See if I can find my phone somewhere, and then at the same time, I want this thing to kind of like be blocked a little more. It's just not the best spot to sit. Hey, how's it going?
I want to reiterate, please join Piazza. I know a lot of you guys like use GroupMe to create like the group to like ask and answer questions. I found out like a better way would actually be like everyone join Piazza, and then you can ask questions and people can answer it. Like if I like have time, I'll answer them like in a timely manner. So like I really appreciate that. I'll share the link again. I see some of you still hasn't joined. So please join it. I think that would be really helpful.
Okay. So let's see. There we go. I'm just back here. And okay, so we talked about the fact that there's no textbook, and we will be using a lot of documents, files, programs, examples, videos, etc. on Elms. There are 2 technologies that we're going to use in this class. These are homegrown technologies, so University of Maryland is a significant school. And I believe as a professor on this campus at the University of Maryland, that is College Park, that we should be competitive with other schools. And so we should not be copyists. We should not get things from, even second and third tier schools in terms of our technology needs. We have to create our own, basically, right? And we don't, as students, you should get the impression that you will be trailblazers. You will not be following things. And I think that's a good sign from, as far as looking at the technologies that we're going to have in this class, you should view them as such, that we create our own technologies and we actually use them. And, we're not talking about some shabby, some, fragile technologies. We're talking about things that are extremely almost commercial grade, especially the second one that we're now working on to actually improve into another edition. So hopefully that will be inspirational to some of you, that you actually will get this same impression that you go to school at Maryland and you are a trailblazer. You're not a follower, but you're a leader. That's, I think, critical for students to have, as an impression from their professors. Okay, so because of that, I've been using things that I have been creating at the University of Maryland, and University of Maryland has been very supportive. This new phase of technology that we're developing, for example, they've been gracious enough to give us some money to further develop it, and I'll share some of that with you later in the semester. Maybe I'll give you a little bit of a sampler today. And so that's what's going to happen. There are 2 technologies that we're going to use. One is called the VESP. That's really the one that some students connect to better somehow, because I think it's just a C code that or C++ code that they come in to, and then they write programs and they test their programs, and because it's something that they can change, the code can be changed by the person who's running it. That makes it somewhat attractive to some students. So I'm basically referring to something like this. For example, this is like one of the editions. This is the 1.0 edition of this VESP technology. We're going to use this all the way to the actually we're going to use all the way to the end of the class, because we're going to have different editions of this, like including kernel, microprogram, interrupt versions of this code. And so this will be, when we get started, we're going to be relying on this pretty heavily, because this kind of describes our technology. This technology kind of describes the organization of the very first computer that I'm going to introduce you to, which is our VESP 1.0. I'll talk about this in just a little bit. Now, once we complete our initial exposure to computer organization, We will then switch to this more powerful technology, which, as I said, we're in the process of. There is a version which I actually shared with you here in the form of a link, or if I didn't, I should have. Let's see, there it is. This is the. I guess this is the place where you have to go to grab it from there, and you have to log into that account. Maybe just let me see what happens if I click on that. Just like you would click on it. Okay. Let's see if this, it gets me. So there it is. Like it's right there in front of you. I just did 2 clicks. Okay. I don't know where that is now. Here maybe. So this will come up on the screen. Okay. So this is the second technology that we're going to use. Now, I've been working tirelessly to actually get this current edition to be available, and we are still working on it diligently, and it may end up being actually available to us. It may not be. I'm not really sure how it's going to work out in the end, but this is already there. This is just like a backup, basically. This is already available, so you can always use this. And this unfortunately doesn't have a lot of, like the helps and stuff, other things like, you probably, nothing comes up in there when you just click on help and things of that nature. Now, what we're doing as we speak, so we're going to talk about this. We are currently taking further steps in order to make things, more effective, let's say. Okay, so in other words, like you'll feel a little bit more complete in terms of your capabilities as far as what you're able to do with this second technology. We're working on this code appeal version of the same technology, which is, I think, in my opinion, probably going to be a leading technology in the end when we actually use it, when we complete it, let's say. And so we're working on this as we speak. And this is a lot more. And I may just use this once in a while. When it comes up, I'll show you what it is. So this is the Code Appeal C, as we call it. And this has got lots of things on it, which the other one doesn't. One of the things it has is what we call the help files. Okay. So you can see that there's a lot of help files. For example, instructions are defined here, exactly how they work. All the instructions are defined, created. It's a very powerful technology. And it has this instruction repertoire, which is pretty much like a combination of all of the existing machines in the commercial world as well as in the fictitious world. So this is a real machine in some sense, certainly a real machine. It's got lots of other bells and whistles that I think a code mill doesn't happen to have. One of those, for example, is something like, let me just open a file. Let's say I'm just testing this. Sorry about, there's something there. And when I get this, this is just, basically this is just a sample test program. One of the things you can do with this, if it actually works, is to, for example, assemble this to what we call a machine code. You can see that that's a machine code. Let me turn this off a little bit. So you can see that that's machine code has been generated from that code that you just saw. And you can actually load this to memory, okay? In fact, you can see that right down here, some other thing come up because this is a machine code. What we can do is we can actually load this directly to our computer. You can see that, we can actually say, for example, load, it'll load that particular code in here now. And this is what's called, let's say make it hexadecimal or binary. You can see now that we actually loaded that program, which was an assembly code, down into these things. Unfortunately, do not exist on CodeMill, but I'll use this. And if I get this completed in time, hopefully you will also put your hands on this thing, and you would actually come to love it. I'm sure that that the ability to see all these different layers that I'm going to talk about in this class will give you this confidence that you're understanding what's really taking place when you organize a bunch of things into what we call a computer. Typically, a computer is about 7 or 8 layers, all the way from the app layer down to the so-called transistor layer. And our goal is to create this technology so there'll be no rival, no equal to it. And so every college in the US and around the globe will end up using this, because every which way they look at it, they won't be able to see anything similar to this in terms of the power, in terms of the versatility, and so on. Okay, this may sound like I'm advertising something. I'm not. Again, I just want to go back to the same thing. You're my students. You work. You go to school at Maryland. I want you to feel like you are part of a big, significant organization that is competitive, and then people who go to school at Maryland can actually make great things. Okay, I'm not talking about myself at this point. I'm talking about you. And as you graduate, as you go on to different and bigger things, you will have this somehow signature in yourself. Okay. All right. Now I've said all those things. Let's get back to Microsoft Word, just so that I say a few more things about other aspects of the class. The assignments. Maybe just I'll go to the Elms place. Let's see. The source code is there, but the source code is also on Elms. Let me see if I could do one thing here, which is to click on my Elms link. So if I go up here and I click on Elms, I guess they'll just give me something to log in with. Okay, I'm just basically showing you all of the things that you would be doing yourself when you actually end up using these places. Some of you may have already discovered what these things are, but others may not. So there is a course site. I think there is a student view. I don't want to sort of like switch to it, but as an so this is like fall 2020. Let's see, where is it? Down here somewhere. There it is, 446. I published this already, so it must be at the very top. There it is. Not that one. I'm sorry. Where is it? There it is, spring 2021. So this is what I was referring to. And the files are here. Lots of files. Some of the things that I talked about are here, like the source code. All of the editions of VESP are here. You can actually bring them to your computer. You can then, Xiaomin will help you, do these things. And that discussion sections are an integral part of ENEE350. And it's very critical that you attend those discussion sections and raise questions, and then get as much help as you can. Now, the other thing, of course, as I talked about, is the video business. So here are the video lectures. Now, if I click on this, it may actually, ask me to launch it, which I'm going to do at this point in time. And all the lectures are there, like starting with the first one, I guess. If I click on this, what's going to happen. It's some video is going to come up, and you will see me talk, lecture basically. And that's what I was referring to earlier on. Now, if this is not enough for you, that you're looking still for more information, you can go to web. You can click on YouTube. Let's say that we just try that for a second. Okay. And then you say, if that, you didn't like what you have already in terms of the amount of information that you have. And let's say that I just say ENEE350. Okay, so there it comes. So now you can play this, and you can see that I'm talking about, the ENEE350. I don't know, you may not hear this as I do.
A short video version of it. And
so you can see that there's stuff out there on the web
that we covered last week.
Okay, so you can see there's a lot of stuff there. That's what I'm saying. Now, if that's not enough, go back here, and this will bring you some video class, as you can see. Okay. All right, so it's all in there, basically.
Instructions.
All right, and then it'll come up now at some point in time. There we go.
2 address instructions.
Okay, so it's going to be very specific, as you can see. Okay. And I'm gonna basically go back here. All right, so that's just like all of the things that you need to have in this class. They are out there. I don't think you'll be short in having information. I hope that like between what I described and what will happen in discussion classes and in lecture classes, you will have all the things that you need to be able to to learn this material. This is not some fictitious material. This is very hands-on. ENE 446, for example, which I'm going to teach also, is a little more theoretical and a little less hands-on. But that's the way that that we design these classes, that we kind of entice you in a way to this sort of material where you feel like you're almost like having a blast in a way. It's like you're having all these technologies, you're kind of spoiled, and then you think about 446, material is a lot more theoretical. But in both cases, whether that's 446 or any other class that I teach, I make sure that I look at what is listed at the University of Maryland's syllabus site. Okay, so if you go on to, if you just go, for example, go to schedule of classes here, UMD. All right, so we're doing everything, legit, basically. In other words, we are following whatever the university says we should do in this course. Okay, so we're not procreating here. Okay, so when I look at what is said here, it says structure and organization of digital computers, registers, memory, control, and I/O. Exactly what I wrote up here. Okay, so when you look at this, that's what you're going to see. Okay. Structure and organization of digital computers, registers, memory, control, and I/O data, and so on. So whatever you see on the schedule of classes site, University of Maryland, is what I'm going to do in this class. And that's what we're obligated to do. We're supposed to cover what the University of Maryland thinks that this course should be all about. I'm not going to change that. And you can see that we're going to do assembly language programming, which is one of the things that I showed you briefly. And elements of system software, we're going to look at kernels, a mini kernel, and all those things. Okay. Subroutines, we're going to take a look at subroutines and how we actually link them with main programs. All of the things that are mentioned in a nutshell, in a sort of concise form, will be covered in this class. I'm not going to do anything, I may do a few things here and there that may just enhance your understanding, but I'm going to be sticking to this UMD syllabus. Okay, that's my goal. Now, the university doesn't tell me that I should go and use a particular textbook or a particular technology to do it with, and that's up to me. And I'm going to use, whatever capabilities I have personally, and also whatever technologies that I have at my disposal, whether I created them or others did, and I'll use those for to convey this concept of computer organization to you. And so from that, I sort of like go to this sort of a tentative list of topics, right? And that's what we want to know. In what sort of like order we're going to follow these things. So in other words, this same thing is that thing that you just saw in the syllabus has been sort of like extended, stretched into something like a little more precise. Okay, so there's a software layer, so it says elements of system software. So that's where it's going to be more like kernels, for example. Okay. And one thing that is not included in there, which I have to tell you, and that's at the very end, and this is one of the things I'm going to do, the performance. But this is sort of like a segue to our ENE 446. This happens at the very end. Now, I know that in other editions of this class, this takes the central, the center stage, if you like. Okay. And it's a style that's okay. I cannot object to it, but in a very particular way of doing things, which is pipelining, sort of like overwhelms the entire class, and then everything else, like is pushed to an aside. And I don't think that's the right way to do it. But every professor is entitled to do whatever they want to do. I cannot object to it because we do respect the freedom of speech in this regard. And it's up to the professor who's assigned to this class. If they think that he's qualified to do it, he'll do it the way that he wants or that she wants it. So that I cannot interfere with. Okay. All right. So of course the universities, have this capability to be diverse in the sense that professors can, provide this diversity of knowledge, and then we orient ourselves towards whoever happens to be the one that we want to, somehow learn from. That's a choice the students make in this case, and that's up to students. All right, and then one other thing that's left, which I kind of skipped, I guess, quickly, is the assignments and exams. It'll really be very, very, helpful to all of us, not just, me, not just Xiaomin, if we can sort of like, move along the class, the material as the two of us, Xiaomin and I, do move, forward. In other words, I understand that, we are living in some very unusual times. That I understand that, everybody, we have some issues, some of maybe some, I hope that that didn't happen, but, some of you may have, uh, you know, had some COVID related problems in your own family, in your relatives, friends, etc. Uh, but still, if you're here and if you're, healthy and, mentally, you can, and sometimes we can turn challenges to opportunities. Like, this is, I guess, the challenge of our time, basically, how to cope with, um, issues of this like a pandemic, for example. I mean, something that came to my mind the other day when in fact it's snowed a little bit last night. I'm sure that you also had that snow in your neighborhood. Well, not everybody, but most students, if we are local to Maryland, you probably would have noticed it. And I just said, if this were to be some kind of a normal campus class, University of Maryland would have probably canceled this class. Now with this Zoom, we have this opportunity. Even if it actually there's a blizzard outside, I can still teach. So you can see that some negatives can be turned into positives. That I'm sure that the universities around the globe will actually take advantage of this, which is to say, they will say, well, look, I mean, we have this Zoom or some other technology, and if there's a snowstorm outside, we're not going to give up. We're going to have professors teach their classes on Zoom on those snowstorm days. So we no longer have to have no classes situation. Maybe no, maybe a lot of people already thought about this. Maybe administrators are thinking about this, and not just us, but high schools, middle schools, elementary schools. So this remote technology provides us now with an opportunity to actually not even lose any time when we teach. And so you can see, you know, that there are all these pluses that we should also draw from adversity and challenge as it's happened in this case. All right, so the last piece, as I said, as I was just beginning to say, had to do with homework, midterm, and final exams. I don't think it's really good for any student to somehow overlook the homework assignments and say, well, gee, I didn't realize it was 35% of the total score that I had to contribute to in order to get a full grade in this class, for example. I mean, so I would say to you, do not delay these things. Now, it does basically not delaying them does two things. First, you secure your scores. In other words, you get your score that is due to you. And the second is the maybe more important part of it is it kind of keeps you with the class because you're doing those homework assignments. You're actually able to keep up with the class. And I know that it's easy to look for a reason not to be able to do this. You normally do this after some time. You say, well, professor, I am terribly sorry I couldn't do it because of X, Y, and Z. I just, I can sometimes understand those things. But what is really critical is that you try to but you try to rely on that sort of an exception that you create in your mind as little as possible. That you really, 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 really have to have that reason that, somehow puts you out of doing your homework on time. That must be an extremely valid reason that you don't, like cavalierly or in some casual way, just say, well, I can't do it because I have to do this. Those are things that I think you should pay attention to, because if you do that, we can all sort of like, ride together. This doesn't happen very frequently, I have to tell you that. I mean, I don't get, half the class do this. I don't even get 10% of the class do this. But students will fall through the cracks, for good reasons sometimes. And I can understand that. I can relate to that. If there's a real serious issue, we can take care of it. But don't, just jump on that sort of like a reason, that exception that you create in your mind and say, well, I just didn't do it because I had all these other things to do. Because it's easy to do that. It's easy to, just sometimes you say, well, I don't want to do it because I have other things to do. But you committed yourself to taking this class and hopefully learning something out of it. And I'll do my best to make sure that I deliver my end of it. But then you also have to, like step up to the plate. That's what I'm just saying. There's only 3 things here, like homework, and which is gradual. We're going to assign homework problems every 2 weeks or so. And then there is midterm, okay? And then there is final. The final is multiple choice. And so it's, the reason that we do it that way is we want to sort of like see how much, general knowledge that you have retained up until the end of the semester. And hopefully they'll stay with you, even if you don't take a second class after this. And also it helps us actually quickly grade things because it's a multiple choice, so we can actually finish grading. Sometimes I think as it will happen this time also, our classes are generally final exam wise, they're actually pushed all the way to the end. Like in this case, it's May 18. My other class is going to be May 19. I think those are last 2 days of final exams. I didn't announce the midterm date. It's sort of like is either just before the spring break or just after the spring break. Typically, that's what happens. More often, maybe after the spring break than before, depending upon how fast we get to our, like midpoint in terms of material that we have to cover. Well, I think I've said all I could say. I talked about the prerequisite. I assume that you all meet the prerequisite, otherwise you would not have been let into this class. And and all the other things. I mean, if you're here, I think some of these restrictions and prerequisites don't really. You should not be dissuaded or distracted by those, discouraged by them. All right, so let me just take a minute and bring back. How is it working so far in terms of technology? Is this working for everybody? Anyone? Zachary, are you there?
Yeah. Oh.
Is it working for you, Zachary?
Yeah, it's working for me.
Okay. How about Maria?
Yeah, everything's working fine.
Okay. So in other words, the screen is okay. How about Joseph and Dan? You guys are okay? Dan, Lee?
It's fine.
Okay. Joseph and Gopal, Krishna, Mahajan?
Working well.
Okay. Very good. Very good. I just want to make sure that, you guys are, I can see your names and some of you have pictures, nice pictures. But I just, Hannah Romanowski, you there?
Yes, I'm here.
Good, very good, very good. I'm not, doing attendance here. I'm just making sure that, what I said has gone out to the virtual ether, I guess. All right. Anyway, so yeah. Do you have any questions, by the way? That's why I really wanted to do this. Any questions?
Professor?
Yes, Kisley, right?
No, Tassine. What will be the nature of the homeworks in this class?
So the homeworks would be somehow when you talk to your name or your little box that come up. The nature of homeworks will be the type of homeworks that you will get. For example, you can actually look at some of the homework assignments there. Maybe not, because I think I may have removed them, because sometimes students get the impression that whatever I copy, I just simply load some of the earlier classes that I, on ELMS to this one. And if I leave the homework assignments there, then students say, well, we have a deadline coming up, but some of the deadline is in December or something. So the first homework will be about hardware design of computers. We're going to have actually this VESP 1.0 machine, which has got some 8 instructions. I'll talk about these things in detail. And then after that, we're going to do some programming exercise on VESP. We're going to talk about some, indexing, all these other things. And once we finish that, I think once the programming side of that, the VESP machine ends, we want to explore. We write basically machine code in VESP. Then we want to go back to this technology that I mentioned to you, where like we will actually see some assembly coding. Okay. And let me see if I can just turn this off. We're going to go to assembly coding. In other words, we're going to look at things like this. We're going to write programs that are actually, like there are lots of programs here. I was just, basically testing these instructions to see if they work. I'll make these available to you also. So we're going to basically use, this is a much more powerful machine than the other one that we would use. And it's got lots of stuff in here. It's got a screen. You can see that this is a computer screen. We're going to learn about this. Let's see if I can actually do this. There are registers in here. It's a programmable architecture. Lots of things will be, and so you're going to have some programming exercises here. You'll be learning about the hardware from the point of view of this technology. Lots of things can be, like you can actually go up to 256 registers here. Lots of registers you can see. It's a very powerful machine, this machine is. Okay. And, depending upon how we approach this, I may just, again, it all depends on, how extensive we want to get on this one. Okay. And so we're going to do assembly, as the syllabus just showed us, assembly language programming. And I'm going to show you how to, like there's this diagram, which I think we just saw briefly. Here is the machine that I'm creating all of this with, okay? So this is, if I could just make it stop here for a second. See if I can do this. Okay, so this is the architecture of this machine called CodeAppeal. So, you normally have some high-level language where you write your programs like Java. We're developing this technology in Java, for example, ourselves. It's a Java code that you just saw briefly when I had fired up from Eclipse. And then we have a compiler, which then generates what we call, this is the translation, the business that I'm going to constantly keep talking about. I'll just simply keep telling you that a computer is nothing but a bunch of translators hooked together. And I will just make my point by showing you how these things actually happen. Now, we don't have a compiler running. We're going to write a compiler, either take advantage of the Unix compiler that we have underneath this architecture, or we're going to write a small compiler of our own. And we're going to get that to generate us an assembly language program, which we already have. And then we're going to run that on a processor, which is the CodeAppeal C processor. It's going to run on it. As I could actually demo it to you, but there's no need at this point. Okay. And what we do after that, we actually use an assembler to create an object code, which you just saw me do it earlier. And that object code can actually be linked and loaded inside a computer. And then it gives us what's called an executable program, which we then execute on a binary edition of this CodeAppeal architecture. Now you turn left this way, then you go to, create an object program after you assemble it. And then you take it, you then translate it to a target object, let's say Intel chip, for example, okay, or some MIPS chip, some Spark chip, some ARM chip, whatever chip it may be, doesn't matter. And then you generate that and you just target it onto that particular architecture. So this is sort of like a complete picture of, computer organization. This is like ENEE350, if you want to think about it, okay? If you understand all these things, all the boxes, and you can put your hands on those boxes, you can actually design some of those boxes yourself. you will really understand what a computer is all about. Otherwise, you'll just be a cursory, user of a computer. And that may be your interest. And I know that, I'm a double E myself, and I know that a lot of students from the double E side of our program, ECE, come into this class, and sometimes they say we don't have any programming background and or interest in. We don't want to program things. We want to do electromagnetic field theory. We're going to do, what do you call it? I mean, like communications, signals and systems things. All right, I understand that. And when I went to school, I was in the communications sort of part of some 12 different programs that I went to, and back in Turkey. And I understand what that means. But believe me, I mean, like as you mature into your own field, whether it's information theory, communication system, VLSI circuit design, or electromagnetic, field theory, you're going to end up more or less, you're going to end up introducing yourself to the world of computers, to world of programming. More or less, you're going to do a MATLAB, you're going to do, this, that, something else will happen in your life. So I don't think there's a way out from there. And then this is people, like, of course, we do this ourselves here in the department. Well, we must have seen a good reason why you should take a class like this, even if you're a double E major, right? There must be a very good reason why people in the department, in the college, in the university thought that as a double E major, you should take a class like this. We're not going to justify that. We can always try to justify it, but that's already written into the books that this is something that you have to learn. And when you learn computer organization, if you just look at this as a piece of hardware, you're just mistaken. That's not what it is. But that's not what a computer is. There's so many layers in this computer that I'm just like communicating through to talk to you, to interact with you, that we cannot just simply overlook. It's just not a bunch of transistors put together. That's not what it is. There's a lot of stuff in there. So we cannot ignore the fact that there's an operating system, which is just nothing but a bunch of programs, a kernel underneath, which is another bunch of programs. Okay. And those, are turned into instructions, which are actually a bunch of programs, which we call microprograms underneath. And finally, you get to those gate signals, and then you just fall back upon what we call ENEE350. Let me just actually switch to now iPad. And any other questions, by the way? I think I answer your question, maybe with a lot more answer that you maybe wanted to hear, but hopefully that helped. Any other questions?
Oh yeah, Professor.
Yeah.
As far as the recorded ones, are we pretty much gonna follow like the whatever was on there?
Yeah. I mean, like mostly, we're gonna try to. Well, I guess it naturally happens because I've done this class so many times.
Right.
I do the same thing all the time, so it's it may be off a little bit, like 20 minutes off, maybe in this video. You know what I'm saying?
Right. No, I didn't. I didn't expect it to be like exactly the same, but I get what you mean. Thank you.
Yeah, sure. I mean, when you watch those videos, you will kind of like get the feeling, okay, that's what we're doing in this class. Okay, that's a good question. I think you want to invest some time in that, and you want to know if that's going to work out for you. I understand that. Okay, very good, very good. Any other questions? Anybody?
I was just wondering if the lectures that we're going to take right now, like and the actuals, are enough, or should we go back to the lecture 19 because these are different?
No. Are you asking about the videos again, Jason? Are you asking about the?
Yeah, the videos. Yeah.
Yeah. So the videos are very similar to what I'm going to do in this class. You can always watch those videos, and and the videos. If you miss this class, for example, for some reason, this is being recorded on Zoom. I guess it's going to the clouds. I hope that it is going to the clouds. Otherwise, I'll just switch to that for the next time. It'll be more automatic. Otherwise, I have to upload it and so on. I don't want to do that. But Zoom provides us that capability, and hopefully, it's going to the cloud. But anyway, so they're going to be there. Either you watch the ones that are actually already on Elms, which I just showed you, or you can watch these. I mean, it's up to you, and I think you can watch both of them. You know, usually when I watch, I was watching somebody, for example, like Gregory Margulis last night. He's a distinguished mathematician who received the Abel Prize, on top of being a Fields, medalist, as well as I guess a couple of other prizes that he got. He's just a brilliant person. I was just watching his interview, and so the reason I brought that up is, I just basically slided my video, like I speeded up, I slowed down, I went back a couple of times. I dug into the, basically interview, because there were some things that I wanted to hear. I'm writing a textbook, and what he says is relevant to what I'm writing. So that's how you do this. Like, you have a video in there. I wouldn't take all my time just to watch it from beginning to end. You move it forward, you move it backward, and then you just zoom in on exactly that thing that you need to know. And that way you can actually use your time more effectively. If that makes sense to you. All right, Yasser?
Oh, yeah. Thank you so much.
You're most welcome. Okay, so anybody, any other questions relating to class? Relating to the class, but otherwise we could certainly get started. In fact, we spend most of the time, as you notice, just to do an overview, which is what I intended to do anyway today. But if no other questions, I guess I explain, I don't know, I tried at least most everything that I want to do in this class, how you're going to be judged in terms of your own performance, all those things. And let me see if I like this technology better. I used to use my, there's something called Mimeo downstairs. That's still too far away from, I think, where our wireless system is, and I didn't, that's why it didn't show up in class in time. When I tried to connect to the Zoom and internet for that matter, it just didn't work because I think I was too far away. We had some good luck with that space, but some I think more wireless boxes are coming into our neighborhood, so it becomes somewhat difficult. So let me just slowly ease into the lecture. I'll just give you a bit of I guess a heads up on what we're going to do on Thursday this week. So so the idea is, and I'm going to save these things, I'm going to share them with you guys also, but it's also on video. I created a folder. I call this, as you just saw me moments ago, ENEE350, sort of like a folder. So our main occupation in this class will be about, one particular architecture, which has been a hallmark, a signature for almost all machines that we have today. You can find some trace of it even in the most advanced, what we call superscalar engines of today, some of the machines that are out there, the multi-core machines, etc. It all began with this thing, which is known as the von Neumann architecture. We're going to talk a lot about this. Okay. So that's something that we're going to talk about a lot. And so what von Neumann architecture is, that it kind of views, let me see if I can use enough space, so otherwise I'll skip to this. Yeah, it's very nice, this thing that I'm using. I think it's called Good Notes. I don't know, you guys may have something more advanced. But the von Neumann architecture is something that kind of like assumes just a couple of things, okay? But the hallmark of it, the main idea of it is what's called stored. Sorry about that. Stored program concept. Okay, so this is really critical. So they are almost synonymous. Stored program concept and von Neumann, who was a giant, who was a polymath, maybe the last polymath of our times. Died in I guess, a car accident in a very unfortunate and early age, or some other reason. Sometimes I read different accounts of his demise. But he was he has his work, his research, his contributions to science have resonated in different fields, in statistics and economics, in computer systems, in quantum physics, mechanical engineering, lots of places. But his main contribution to us is this idea of stored programs. Now it looks so natural to us that programs, as you just saw me, show a part of memory in our code appeal, where we could just dump a bunch of bits in there and then execute them. This is so natural now, but at the time that he did all this stuff, which dates back to late 1940s and early 1950s, people did not know exactly how to proceed. And I don't want to give all the credit to him in this regard. So there are some other people, working on things. Zeus in Germany, for example, is one name that comes up. And then ABC Computer at Nassau Berry Computer, ABC, that was dubbed as because of the two people, one the professor at the Nassau and the Hungarian, I guess, computer scientist, if we could call him that, because I'm mostly maybe a mad person. And then and Berry was a student, so they call it an ABC Computer, C4 Computer. And there are other people, Stibitz at AT&T Bell Laboratories, for example. He just built a small computer on a breadboard of some layout, maybe. But I think the idea of this is sort of like almost similar, akin to like how people switch phones in the early days, after Alexander Graham Bell invented the telephone in 1876. It took a while for people to actually go to these automated systems that you would have an operator, and operator will just put those jacks in and out of places, and then you'll end up having your connection with that party that you wanted to talk with. So it was like manual basically, as opposed to automated. So the store program concept was introduced by von Neumann in the same sort of like way, and so that computers can do their own business, can execute programs without us, basically holding them by hand. I mean, that was the whole idea. Okay, that's what made this store program concept relevant. So what that meant was that you would store a program or some programs. Let me just do it this way. I think it'll be a little easier if I just did it this way. You would store a program inside a computer's memory. Okay, so this will be like memory of our computer. Okay, I'm just getting used to this new style of like writing notes. Okay, and then you will have these locations, like this could be the topmost location. Okay, this could be the next location there, or maybe location in between, etc. And these locations there. Sorry about that. It's hard to get this out of there. I'm still not really good at this. But down here somewhere, you will have your program. Okay. Our computer program will be there. Everybody else, you can divide the computer's memory into a bunch of places, and this will be one such place. And so what we have to do, this store program concept, now that we stored it into memory, we would like to simply set something called a program counter to this place, and the program counter gets advanced every single time to go to the next location, next location, next location. And if you, for some reason or another, you want to jump back to here, then you have an instruction which is called the jump instruction, which is going to bring you back in there. So he worked out all these things in his mind, and he said, hey, here's what you have to do. Just put this stuff into computer memory and simply have some system, which we now call a sequencer or a controller, take care of business. So next to this memory, we had something called a CPU, which is this von Neumann architecture. Okay, so we have this CPU. Sorry about that. We had this CPU here. What happened? I need to really get used to this. Just have to be a little slow with it. Okay, so this is CPU. CPU. The CPU would then interact over some bus with this thing. This is called, a bus. Could it be called a data bus or an address bus? You can have two buses. Okay. So these are buses, basically. So now we put two things together, right? And then you wanted to, interact with the outside world, so you would actually bring something else into this. Okay. Then you may have a computer monitor, for example, like I just showed you. That's why I actually put the screen in there when we did this, technology, right? You just saw it there. If I could ever bring it, it's actually behind this. If I turn this off, you'll see it. It's right there. That's the screen. That's the computer screen. And that's what I'm going to draw now. So I'm actually using the same idea that, von Neumann gave us. I'm just simply following his footsteps. Okay, computer screen. It's a monitor. Okay, we also need something that will actually have to enter something into this, computer. And so we need something like a keyboard, which you see that, I have on my MacBook, and also have a keyboard here. So these things haven't changed in such a long time, okay? So let me just do that also. So here's a nice keyboard. Keyboard. And it kind of goes in this direction. Does that make sense, everybody, so far, right? We have programs inside the memory. We got this monitor. We got the CPU. And we got the keyboard. I mean, you can have a scanner. You can have a printer. You can have lots of other things. That's the von Neumann architecture. But most specifically, and I had to really stop this class in very quick order. I just realized I have to power this up, and I have to bring my other cable in there before we actually totally expire. And we only have 3 minutes of class left. But let me just say this: the store program concept is what rides and what drives this thing. And when we come back on Thursday, I'm going to talk about the CPU, which, let me just give you a little bit of a preview very quickly. Basically, it is like a bunch of, not a bunch, but three things put together. The CPU is like this. So this would be fetch. This would be decode. This would be execute. And we will have these directions. Back to here. Okay. So that's what we're going to learn. And we're going to do this in the context of a machine, which is called VESP. Von Neumann architecture. It's an E in there somewhere. Okay. All right, so I think this may be a good time to bring our class to an end. We did mostly an overview of what we're going to do, but then towards the very end, in the last few minutes, I brought us to this place where we're going to be looking at this thing called the CPU. that one right there. And we're going to open that up. Of course, we're going to have to, involve the memory. We're not going to be looking too much into the monitor area. For that, we're going to need what's called a frame buffer or a video RAM, which will kick in when we actually look at the kernel layer of this machine, as well as the code appeal that I mentioned to you. And we'll also have this keyboard come in when we actually look at the code appeal. We want to have this keyboard in the VESP architecture. That's why I introduced the second one, which is the one that is called the code mill or code appeal. So I'm going to rest my Apple Pen right next to my iPad. This is what I've been using, by the way, in case you want to know what it is that I'm actually doing. Some of you may be taking notes already this way, okay? And whatever I'm doing here, and I have to sort of like, maybe knock or like, maybe kind of say something bad about Apple. Apple has something called screen sharing or screen mirroring. You can actually mirror this iPad to a TV unit. You can put this thing onto a TV screen, but you cannot put this onto a MacBook. So I had to pay about $17 for a piece of software called Reflector Teacher Edition to be able to do this. And Apple has that nice capability. If I could just show this to you, those of you who might actually be interested in this, there's something called like this here. You see that? And I'm being shared right there. Do you see that? You saw that, right? Briefly. You see that we're talking here through that thing right there. I don't want to touch on that. That's just like turning on and off, or like blinking in a way. That's what makes this possible. So if I actually do this, that thing that you see on your screen will not show up unless I use this thing called Reflector Teacher. And that is as silly as a company may get. I'm talking about Apple. They're able to put this iPad on a TV screen, but they're not able to put it on a MacBook. They have the opposite. I can actually get that computer entire, my MacBook screen, on my iPad, but what am I going to use it for? It's useless for me. What I need is a pen that's going to write on an iPad, and that thing will be visible to you as it is now. And so, you can see that sometimes even big companies can miss it completely. They just thought that Apple iPad is only good to go on a flat screen or someplace, but not, because they were thinking nothing but video again. Like you can do another video, you can do some sound, AirPlay, etc., all those other things that they're doing. They never thought about a professor wanting to use that Apple Pen on an iPad to come up on the screen like you're sitting now. It was just, they were this close and they missed the bus big time. And I'm glad they did, because this little known company called Squirrels now are able to actually do all the things that they're doing and maybe making some money out of it too.
Professor,
yeah,
you might want to try share screen. There's actually a way you can share like your iPad screen. I wonder like if you can just use like Zoom to do that.
Say it again. Well, I don't want to use my iPad directly on Zoom because I want to, I don't want my iPad to be in my face.
Okay.
So if I use, yeah, I can Zoom from my iPad. But then I'll be looking at my, there's not enough bandwidth on this iPad.
Oh, okay.
So that's why I split the work between the computer and this. Yes, there's a Zoom option there.
Yeah.
The Zoom steps in when Apple left it out. That thing that you see there kind of blinking a little bit, like graying out, that is what's making this happen. This is called mirroring. I'm mirroring now iPad thanks to this app on my computer. I would not have been able to do this if I actually was left to Apple alone, which is such a huge company. $1 trillion, dollars worth of company cannot even fix something this simple. And I'm a diehard Apple person, but I'm angry. Okay.
Okay, cool.
All right, everybody. So I guess I'm going to see you guys on Thursday. I hope that everything works out for all of you, that, you commit yourselves to this class. And I think we're going to have a great ride. Just buckle up and get ready to learn some new material. So with that, I'm going to sign off because I have to recharge the two computers, the iPad and the computer, for my next class.
Hey,
yeah.
I'm just curious. Who was it again? I missed that. They died in the car accident. Was that von Neumann you said?
Von Neumann, yeah, John von Neumann.
Oh, right,
Von
right.
Neumann, yeah. I
Yeah,
think
I thought you
there,
said someone else there.
there there are some other renditions. I think some people think that he died of cancer, but there are different. You know, I wasn't there to know exactly what happened to him, but you know,
Right.
but take a look at it and let me know, exactly what you find about it. But those are the two reasons that people actually. But
Yeah.
he was a brilliant man. He actually was Hungarian. He studied chemistry. He went on to Germany and on to the U.S. and then to Princeton, IAS, Institute for Advanced Studies. And he's, like sometimes once in a while, let's say, as societies, we benefit from the brilliance and ingenuity of people of his caliber. And Gregory Margulis that I was talking about is another giant, but in a different way, not a polymath. Like, Euclid would
All
be
right.
a polymath, and Archimedes would be a polymath.
Yeah, because I looked it up and it said like cancer because of like radioactivity or something like that. Probably because of radioactivity.
Yeah, most likely, because he was in all over the place. He was in that era, like the Second World War. He was in the U.S. and so on, all that stuff. All right, so
It's kind of interesting.
Yeah, it's kind of interesting. Yeah, I am a sort of history addict, I guess, a buff or whatever, and I like to look at the science and history of science. And there's a book by somebody called T. Bell who actually lists all the greatest mathematicians of all times. And I have a copy of that book, and I look at those things once in a while. I don't want to see my computer die in front of me in terms of power. You can see that's actually 13%. Maybe I don't know if you can see that too, but it's kind of reddish there. And so I'm gonna I'm gonna say goodbye to everybody and bring the class to an end. And
Right,
please
see.
keep, yeah, yeah. So keep coming to class. If you don't, if you can't, watch my videos. And I think we're going to be in great shape, and hopefully everything will work out for everybody. And just stay safe, of course. Most importantly, stay safe. Okay. All right. I'm signing off. Take it easy, everybody.